Hey guys, my name is Trevor Sullivan and welcome back to my video channel. Thanks so much for joining me on another video where we're going to continue our learning about the Rust programming language. Make sure that you check out the playlist for this particular topic. You should be able to find it in the description or in the comments down below. I'll go ahead and just pin that to the comments so that you can easily find it, and that way you can follow along with this video series. In my last video, we talked about how to set up the Rust tool chain, which consists of the Rust compiler, the cargo CLI, the Rust formatter, and other things like that. And we installed that on a remote Linux environment. And that's exactly what I'm connected to here in my Microsoft Visual Studio Code window. Now, what we talked about in the last video mainly covered installing the tool chain, but we also wrote some really basic code to make sure that we understand the entry point to an application, which is the main function here. And we also wrote a simple test function here so that we could just call out to some other function and print out some text, right? So what I wanted to cover in this particular video is a lot about the core data types that we have in Rust programming. When you start dealing with more complex constructs, those constructs are typically made up of the core data types that are provided by the programming language. So we're going to learn about things like integers and floating point values and strings and things of that nature. And hopefully by the end of this video, you'll have a better understanding of how these data types work inside of the Rust programming language. Now, for starters, I wanted to point you to a special type that is available in the Rust programming language, which is called the unit type. And yes, that's unit, U-N-I-T, and basically all it is these empty parentheses here. Now, in a lot of other programming languages, like Python, for example, this might be represented as something like a none value, and in some other languages, they represent this as like an empty array type of thing, but it's not really aligned with any of those. It's basically a singular value, but it's just completely empty. The best way that I typically think of the unit type in Rust is kind of like a database field where you can have a null value, which would be similar to something like void in a C programming language. But then you can also have an empty string value, just an empty value in a database field. And that is kind of like what I think of the unit type as, where it's just this empty value that doesn't contain anything. So this is actually its own data type in Rust. And even though the syntax looks really weird here, what I'm doing is declaring X as a unit type, and I'm setting its value to the unit type. So if I try to declare X as a unit type, but assign something like a integer to that unit type, you're going to see that the compiler is complaining because it expected the unit type, but it actually found an integer value. So that's the unit type. Let's talk about integers a little bit. So in Rust, we have a couple of different types of integers, just like most other languages. And if you're looking for documentation on the core data types, I'd encourage you to check out the official Rust programming language book, or you can also check out the Rust reference documentation, which goes into a lot more depth about the different data types that are available in a very structured fashion. So what we're going to do is start by looking at the integer types here, and you'll see that we have a couple of different types of integers. There's signed integers and there's unsigned integers. So in the case of an 8-bit integer, let's compare the difference between an integer and an unsigned integer that's 8 bits long. Well, remember that in base 2, a bit can be either 1 or 0. So that's the base 2 numeric system, unlike base 10, where you can have 0 through 9 as any valid digit. But in base 2, we only have 0 or 1 for each position inside of our integer value, right? So basically, the very first bit of that integer can be reserved for a positive or negative sign, right? And so what that does is it cuts down our 8-bit integer from 8 bits down to 7 bits. And so that limits the number of or I should say the range of the numbers that we can assign to an integer value. So with a signed integer, we can have either negative values or positive values, but with an unsigned integer, we can only have positive values because there is no reserved bit to indicate whether it's positive or negative. But what that means is that the unsigned integer, because it's not reserving that eighth bit to indicate the sign, we actually get an additional range on our numeric values. So you can have a larger value, but it can only be positive with an unsigned integer. So let's take a look at an example here. So I'm going to assign a variable here called x, and we're going to set this to a signed 8-bit integer, which is just I8 for short in Rust. And if we set that to a value like 5, and then tack on a semicolon here, let's save our code. And as you can see, everything compiles just fine. Now, if I set it to U8, short for unsigned integer, 5 is still a valid value. But now, what if I try to change this back to an I8 and set a negative 5 value? Well, because a signed integer allows me to set negative values, that works perfectly fine. But if I change the data type to an unsigned integer, remember that unsigned integers can only have positive values because that additional bit is not reserved for indicating positive or negative value, right? So as you can see, we get an error here from the compiler indicating that this value cannot be negated. So if we change it back to a positive value, like let's say 255, that works perfectly fine. But remember that the range of a signed integer is limited because one of those bits has been taken away to act as the positive or negative sign, right? So if we try to set an I8 as the value of 255, then you're going to see that we actually get this message saying that this is out of range for a signed 8-bit integer because we only have 7 bits available for the actual value. So unsigned integers can contain larger values, but they don't have positive or negativity, right? So as you can see, we have unsigned and signed integers here, and we have 16 bits, 32 bits, 64-bit, and 128 bits. So you can kind of reserve different amounts of memory. Generally, you want to stick with the smallest size possible for your application, just so that you're not wasting memory on values that aren't necessary. Like if we're just going to assign a value of 0 through 100, it doesn't make sense to reserve 128 bits or 64 bits or 32 bits for that value. We could probably get away with just an 8-bit integer. All right, so now that we've talked a little bit about integers, let's talk about floating point values. So if you need to have decimal values in your applications, we can use floating points in order to accomplish that. So let's check out our numeric types over here in the reference documentation. And as you can see right down here under floating point types, we have F32 and F64. So we only have 32-bit or 64-bit floating point types. So if we come back to our application here and change x to an F32, you can see that in this case, the value of 255 is being interpreted as an integer. But if we do 255.0, that indicates to the Rust compiler that we have a floating point value rather than a whole integer value. And the value 255.0 could be assigned either to a 32-bit or a 64-bit floating point value. Now, what would happen if we tried to, let's say, subtract an integer from a floating point value? Do you think that that's going to work? Well, let's try. So we'll do let y, and we're going to set y to an I8, and let's actually do unsigned 8 here, and we're going to set it to the value of x minus 5, okay? So if we save this, you can see that we get this exception here because we can't take an integer value and subtract it from a floating point value. In order for us to do any kind of mathematical operations, we have to make sure that we are using the same data types for each of these values. So in this case, you can see that even though we get a warning about the unused variable y, the compiler does still allow us to subtract 5 from an unsigned 8-bit integer. So just keep in mind that when you're doing mathematical operations, you need to do them on the same data types. And that brings in another topic, which is type coercion. Now, type coercion is also known as casting in some other languages, like C# is, they call it casting. But essentially what you're doing is you're converting one data type to a different data type. Depending on what type of data it is that you're converting, you might either be allowed to or disallowed from doing those type conversions. So let's go back and say that we had a 32-bit floating point value of 255.0. Well, once again, we get this error about the mismatched data types here because we can't subtract an integer from a floating point value. But what we can do is basically coerce x, which is a floating point value, into an integer value instead. So what we'll do is say x as u8. And when we use the as keyword, we're basically saying that I want you to take the value of x and I want you to coerce it or cast it or convert it to an unsigned 8-bit integer, and then it will do the mathematical operation because it's now interpreting x as an unsigned 8-bit integer rather than a 32-bit floating point value. And so now if we were to print out the value of y here, let's do a cargo run, you can see that we get the correct value of 250, 255 minus 5, right? All right, so we've got floating point 32. We've also got floating point 64. Of course, if we do that, we're still going to be able to cast the 64-bit floating point value as an unsigned 8-bit integer. So that's still going to work just fine, regardless of what size floating point value we have. All right, so those are integers and floating point values. Let's talk about Boolean values next. So Boolean values are just really simple. They're either true or false. It's either on or off, right? And so Boolean values are really easy. So let's just do let old, I am old, equal to true. So if we save that, you can see that the Rust compiler here infers that the data type that's being assigned to this variable, I am old, is a Boolean data type. That's not actually in our source code. It's just being displayed by the Visual Studio Code editor here, but you can be more explicit and actually specify bool as your data type here. So you can either do inferred values in the editor where it just kind of displays the type to you, or you can actually commit that to your code right here. So for Boolean values, we could just take that existing variable and we could set it to false, but watch what happens here. As you can see, we've got I am old, it's a bool, and it's set to true. Then we change it to false. And let's try to print out the value of that variable. All right, so we'll print out the value of I am old. We also need a semicolon right up there. But check out what happens. We get this exception that says that we can't assign twice to the immutable variable I am old. And I didn't really want to get into this quite yet, but with variables, they are immutable by default, which basically means that they cannot be modified. They are concrete values. So in order to make a variable into a value that can actually be modified, we actually have to turn the variable from a default immutable variable into a mutable variable. And the way that we do that is with the mut or mute keyword here. And that indicates to the Rust compiler that we want the variable called I am old to have a changed value. So now the compiler allows this to run just fine, and we update the value of I am old from true to false, and then we print out that value in our terminal down here. So just keep in mind that anytime that you reassign a variable to a new value, you need to make sure that that variable is mutable. Otherwise, you'll get a compiler error indicating that that variable is immutable by default. All right, so that is Boolean values, either true or false. And so now let's talk about strings. So we actually have a couple of different data types when it comes to text data. We have a character type, and we also have a string type. And the Rust compiler is going to look at the type of quotes that you use to determine which data type it is that we're dealing with. So let's say that we have a string called mystr, okay? And I'm going to set that to a value of capital A, and we'll put a semicolon there. And then we'll just do a print line and specify these curly braces and pass in mystr. Now, as you can see, the Rust interpreter here has determined that this is a character type because we have single quotes around it. But if all we do is change these single quotes to double quotes and resave our application here, you can see that that changes to a pointer to a str string object, right? And so the single quotes indicate a standalone character. The double quotes indicate that we have a string value. So let's go back to turning this into a character. Now, what would happen if I tried to assign multiple characters to a single quoted character string, like AB? Well, as you can see, character literals have to have only one character inside of them. These characters are actually 4 bytes in size, so we can only fit that much data inside of there, and they're interpreted as Unicode values. Now, one interesting thing that you can do is you can insert emojis inside of these characters here, at least sometimes. So let's try to put a fire character in there. And if we do cargo run, you can see that we were able to save that fire character as a value inside of a character and then print it out using the print line macro. Now, strings are a little bit different than characters, right? Because strings generally have variable length. It could be a first name that's anywhere from maybe 3 characters all the way up to 20 characters or something like that, right? And with Rust, we actually have a string pointer by default. So there is a separate string data type in Rust, but we are going to just focus on the string pointers for now. So let's do let first name equal to double quoted Trevor, okay? And then we'll just copy this down here and put semicolons after these, and then we'll print out the first name variable. All right, so let's do a cargo run, and you can see that our string is printed out just fine, right? Well, what would happen if I said first name is equal to Bob? All right, so as you can see, we get this error once again saying that we can't assign twice to an immutable variable because a string pointer, just like a numeric value, is going to be immutable by default. So we have to turn it into a mutable variable by using mut. And then we get this little warning just saying that the initial value is never being read because we're just setting it to one value and then we're immediately changing it without actually using it. So one thing we could do to mitigate that would be just to put another print line macro statement right there. So now we're actually consuming the value Trevor from some expression, and then we change the value of that variable, and then finally we print it out a second time. So if we do cargo run, now we get Trevor and Bob. And so that's how we turn a string pointer into a mutable variable, right? Now, something else that we can do is work with a data type called a tuple or tuple. I'm not really sure how you say that, to be honest. I've always said tuple, but I hear a lot of people say tuple. So a tuple is basically just, it's kind of like an array where you can have multiple values. But what's interesting about a tuple is that you can actually have different data types inside of the tuple, whereas with arrays, you actually have to have the same data type as each member of the array. So let's try creating a tuple. So let's do let name, and we'll set it equal to a tuple, which is going to use parentheses. Initially, it looks like it's just a unit type, but inside of the parentheses, we're going to do Trevor, comma, and then Sullivan, and we'll put a semicolon at the end there. So we declare a tuple by simply using the parentheses, and then we use a comma to delimit the different instances of data inside of the tuple. Now, if we wanted to, we could also pass in something else like age of 40, right? And 40 is being interpreted by default as a 32-bit integer. And so now this tuple contains one string pointer, 2 string pointers, and a signed 32-bit integer. But we could also cast this and say, well, I actually want this to be an unsigned integer. So we can do type coercion here to turn the number 40 from an integer 32 to an unsigned 8-bit integer instead, and that'll save us a little bit of memory, right? So now what we can do is go ahead and just say print line, and if we try to print out this tuple here, let's see what happens. Well, as you can see, we get this formatter error right down here because the formatter doesn't know how to print out this tuple value. Instead, what we can do anytime that we run into a formatting error like this is we can actually just do a question mark, and this will use debugging type output instead of the default formatter. And so if we try to run our application again, now you can see that it just prints out the value of the tuple itself, exactly the same as it looks in our code here, minus the type coercion, right? So that's a little trick that you can use to print out values that don't want to cooperate with the default formatter. All right, so that is a tuple. You can see we can use different data types in there. Now let's talk about an array. So let's say that I had an array of ages, people's ages. All right, so I'm going to create an array called ages, and this time we're going to use square brackets instead of the parentheses. And so I'll put in an age of 40, 45, and 50, and then we'll put a semicolon at the end. And as you can see, the syntax that is inferred by our editor here is that we would specify an integer 32, a semicolon, and then the number of elements inside of the array. So if I wanted to, I could go ahead and plug that into my actual code here and say, I want this array to be 32-bit integers, and I want there to be 3 values inside of this array. Also known as the size of the array is 3 different values. But because 40, 45, and 50 could all fit into something smaller, I could say I want all of these to be an unsigned 16-bit integer instead of a signed 32-bit integer, and that will simply change the core data type of this particular array. But remember that unlike tuples here, arrays cannot have multiple different data types. So if we try to put in a string like Trevor here as a 4th element, well, we have 2 different problems. First is that the size of the array can only contain 3 elements total, 0, 1, and 2. And the second problem here is that because the array's data type is an unsigned 16-bit integer, we can't put a pointer to a string value inside of this array. So of course we have to remove that string pointer value, and now our array is valid. So let's just do another print line here, and we'll plug in our braces, and then we'll pass in ages here. And then once again, we're going to get this error message about the default formatter. So we'll use debug output with question mark here, and that will change it to print out the actual code style for the array definition. All right, so we've covered quite a bit so far. We've covered integers, floating point values, Boolean values, string pointers, I should say, as well as tuples and arrays. So what else do we have here? I think the last thing I wanted to cover in this video is slices. So slices are kind of similar to arrays, but they actually point to arrays. So if we head over to the Rust reference here, let's take a look at the definition of a slice type. As you can see in the Rust reference here, a slice doesn't actually own the data that it points to. It simply borrows it from the type that it's pointing to. So let's go back to our array of ages right here, where we have 3 different values inside of this array. Let's actually add a couple of more values here. So let's do 55, 60, and 65 as well. So we have basically indices 0 through 5, right? And I'm going to bump the array size up to 6 elements to accommodate those extra values. And so now let's say that we wanted to grab only the second, third, and fourth values of this array. So how would we accomplish that? Well, what we can do is say let new ages equal to a pointer using the ampersand to ages, and then we want to basically grab a range of values. So to grab the second value, that would be index number 1, which is inclusive. And then we use the ... here to indicate a range, and then we would specify the number 5, which is exclusive, actually number 4, which is going to be exclusive. So now what we can do is print out this value here, and we should see values 45, 50, and 55, because the index number 4 by default is actually excluded, even though that's the number that we specify as the upper end of the range here. So let's do a print line, plug in our curly braces with the question mark, and we'll pass in new ages. And if we run our application here, you can see that sure enough, we get 45, 50, and 55. So even though index number 4 from this array, which would technically be the value 60, is specified here, that by default is exclusive. If we want to include that upper range value of our slice, of our array, I should say, in our slice, then what we can actually do is put an equal sign right before that number, and that will include the index at that position. So if we do cargo run, now we get that additional 60 value being included in our slice. So the slice points to the array that has 6 elements, but the slice only includes 4 elements out of those 6. And so if we were to bump this up to 1 to 5, then we would get 45 through 65, and we're just leaving off the number 40. Or if we start at index 0, then we can get an exact copy of the data that is inside of that array. So those are most of the core data types that are built into the Rust programming language here. As you can see, we don't have any use statements at the top. We don't have to import any additional libraries or anything like that. These are just some of the core data types that are available in Rust. Also, we learned about mutability, how variables are immutable by default. They can't be modified. But if you use the mute keyword here, you can actually turn an immutable variable into a mutable variable so that you can change the value of that variable. We'll talk a lot more about Rust in upcoming videos, but if you learned something from this video, please leave a thumbs up on the video. Leave a comment down below. Let me know what you thought of this video. Make sure you subscribe to the channel and follow the Rust programming playlist on my channel so you can find more great videos about Rust just like this one. Thanks for watching, and we'll see you in the next video. Take care.